Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on the confidence interval on the mean using the t-distribution. I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos. Distribution of the means. To begin this video, I will make the assumption that you have already talked about confidence intervals and have used the z-distribution to construct your interval. When we have a distribution of the means or sample means, we have two types that we will be looking at, and what we want to discuss now is what is a z-distribution and what is the t-distribution. What are the things that make them similar and what are the things that make them different? When we're looking at the z-distribution, our assumptions that we have to know that we're in a z-distribution is that x must be normally distributed and sigma must be known. For a t-distribution, our assumptions are x is normally distributed and sigma is unknown and approximated by s. Our formula for a z distribution is x bar minus mu over sigma divided by the square root of n. Our formula for the t-distribution is t equals x bar minus mu over s divided by the square root of n. Notice that the formulas then are very similar. They are actually the same except one is z and one is t. The difference is, if I read them, they're the same if I read them as the sample mean minus the population mean divided by the standard deviation over the square root of the sample size. The difference between the formulas is one is using the population standard deviation and one is using the sample standard deviation. One is for the z distribution and one is for the t. But the process for each is similar. We take x, the sample mean, minus the population mean, over the standard deviation divided by the square root of n. And if you can keep that in mind as you're using them and applying them, that will help. Notice under the t-distribution we add a new phrase, degrees of freedom. Degrees of freedom is n minus 1. And if you're looking for someone to explain to you the deep mathematical proof of what degrees of freedom are, you've looked to the wrong video. I'm going to show you how to use degrees of freedom, but I'm not going to give you the explanation of them. That is not really necessarily a hard thing, but it gets a little complicated. And for our purposes, if you'll just go with it for now, it makes life a little easier as we present this new material. Again, notice the only difference between the two formulas is the difference between sigma and s, between the population standard deviation and the sample standard deviation. And again, degrees of freedom are n minus 1, the sample size minus 1. Look at the shape of the z-distribution. It is a normal curve, and as we talked about before, it's just a plain normal curve. As when we talked about the sample means, the z-distribution did get narrower and taller as the sample size grew larger, and as our standard deviation got smaller as our sample size grew larger. Our t-distribution, notice, is a slightly different shape. It is shorter and wider. Now let's look again at the shape. We have, for degrees of freedom, of 6, our graph may look something like this. Notice that these are exaggerated graphs and they're not necessarily drawn to scale. We have another t-distribution with degrees of freedom of 11. Notice the change in shape. And a third t-distribution, degrees of freedom for 22. Notice the shape of it. Compare the shapes of your t-distribution to the graph of our z-distribution. The t-distribution is shorter and wider than the z-distribution. As the degrees of freedom increase, the t-distribution gets closer and closer to the z-distribution. We need to learn how to read the t-table. It would be best if you had a t-table in front of you at this point. If you do not, pause the video and go get one. You should be able to find one in your textbook. If you do not have one, you may go to Google or try to find one online by going to Google or whatever you used for your search engine and search for t-distribution table. When I did a Google search, a PDF version of the table was my first search result at the site that you see on your screen. But any t-table will work. I assume now that you have your t-table and we're ready to find t sub alpha divided by 2. This is very similar to finding z sub alpha divided by 2. And we're going to do this one for 95%, two-tailed, and n equaling 10. Our alpha is 95%. That leaves a 5%, since we're doing a 95% confidence, that leaves our alpha to be 5%. That's the amount we're willing to risk. Since it's two-tailed, we will divide that evenly among the two tails. Our degrees of freedom, notice that we have used our abbreviation. Math teachers love to abbreviate, so DF stands for degrees of freedom. Is n minus 1, 10 minus 1 is equal to 9. So we're going to be looking for the t alpha divided by 2. Drawing your curve gives you a feel of what is happening and keeps you straight about a lot of things. My advice is not to skip this step. So we have our curve. Take your 5%, divide it by 2. That gives me 0.025. And we want to put those on both sides. And we're looking for the t alpha sub 2. And that is the area to the right, or 0.025 to the right. So we are looking for the number of standard deviations from the mean that this t-distribution, or this value, will represent in the t-distribution. This will be different from the number of standard deviations on a z-distribution. It is first based on the degrees of freedom. So you will look down that column, the degrees of freedom column, and stop at row 9. You will go over until you see the two tails of 0.05, if that's the way your table is marked, or the area in the right tail of 0.025. My table that I happen to be looking at right now is marked as 0.025 in the right tail. Miss Borlaug based this one on one that labeled two tails as 0.05, and then underneath it I think it says 0.025 in the right tail. So look at your table. It should be very easy to figure out. It'll either say 0.025 in the right tail or two tails as 0.05. Notice that that would mean the same thing. And you'll go down and you should see then 2.262 where that row and that column intersect. That gives us the t sub alpha divided by 2, or T sub 0.025 as 2.262. Here is a class activity for you to try. And here is the answer. Remember, show your work and use your table. And here is a quick history lesson to wrap this video up. William Gossett developed the student t-distribution. And when people develop a new idea, it's often named after the person. Why is it then that we call this distribution, the t-distribution, the student t-distribution? We have Einstein's theory of relativity, Newton's law of cooling, René Descartes developed the Cartesian coordinate system. Why is it called the student t-distribution? Well, again, William Gossett, born 1876 and died in 1937. Why isn't it called the Gossett distribution? Well, Mr. Gossett was employed by the Guinness Brewery in Ireland. He needed distributions for small sample sizes, which is what we use this distribution for. He developed the t-distribution, and as a brewery employee, he was not allowed to publish. So he published anyway under the pseudonym Student, and that is why it is called the student t-distribution. And as this is a good place to end the first part of this series of videos, in the next video we will work on a confidence interval on the mean using the student t-distribution. Thank you for watching.